For most of us, the solar system looks the same way it did in school. A sun on the left, planets in a line stretching to the right, everything flat, everything horizontal, everything sitting on the same invisible surface, as if gravity had decided, by universal agreement, that down was the same direction for everyone. That image has a name. It's called the ecliptic plane, and it's real. But it describes roughly the same proportion of the solar system as a single sheet of paper describes a library. Space is not a map. It is a volume. The flatness has a genuine physical explanation. 4.5 billion years ago, before any planet existed, the solar system was a slowly rotating cloud of gas and dust. As gravity collapsed that cloud inward to form the sun, angular momentum flattened it. The same physics that stretches a spinning disk of dough. The large planets formed within that disk and have largely stayed there. Jupiter, Saturn, Uranus, Neptune orbit within 1 or 2 degrees of the same plane. That's where the classroom diagram comes from, and that's where its accuracy ends. The cracks appear almost immediately. Mercury orbits at 7 degrees to the ecliptic, not a small deviation on astronomical scales. It spends much of its year diving below the plane and climbing back above it. The Sun itself is tilted 6 degrees relative to the planets it governs, a misalignment that hints at something violent in the solar system's early history. And look at what we've placed in orbit around Earth. If the solar system were truly flat, our satellites would form a neat equatorial ring. Instead, if you could see every orbital track simultaneously, Earth would appear to be sitting inside a tangled ball of yarn. Satellites crossing at polar inclinations, diagonal angles, intersecting planes at hypersonic speeds. Go further out, and the flatness deteriorates further. Pluto orbits at 17 degrees to the ecliptic. Eris, the dwarf planet that helped end Pluto's planetary status, orbits at 44 degrees. From Eris, the plane of the solar system isn't a surface you inhabit. It's a glowing disk you look down at from a steep angle. The Kuiper belt itself isn't a flat ring. It's a three-dimensional torus, its shape sculpted by billions of years of gravitational interference from Neptune pushing objects up and down out of any common plane. And then there is the Oort Cloud, roughly a light year from the Sun, a distance Voyager 1 hasn't reached after nearly 50 years of continuous travel. The geometry of the solar system abandons flatness entirely. The Oort Cloud is a sphere, a vast hollow shell of trillions of comets surrounding the solar system in every direction simultaneously. Jan Oort inferred its existence by studying long-period comets. Unlike asteroids, which arrive from the plane of the ecliptic, these comets fall toward the Sun from every conceivable direction, from above, below, sideways, diagonal. The only geometry consistent with that omnidirectional rain of ice is a shell that completely encloses the solar system, not a disk, a sphere. If you could see the solar system from outside, truly outside, far enough to see the Oort Cloud, you wouldn't see a flat spinning plate. You'd see a vast hazy ball drifting through space, with all the familiar planets and their carefully ordered orbits occupying a tiny flattened core buried deep inside it. The scale of that shell is worth sitting with for a moment. The Oort Cloud begins at roughly 2,000 astronomical units from the Sun, 2,000 times the distance between Earth and the Sun, and extends outward to somewhere between 50,000 and 100,000 astronomical units. The inner edge is already so far from the Sun that sunlight takes weeks to reach it. The outer edge is nearly halfway to Proxima Centauri, the nearest star. The entire span of human space exploration, every probe we have ever launched, every orbit we have ever achieved, everything we have ever physically touched with a machine, all of it fits inside the innermost fraction of 1% of the solar system's true extent. The comets drifting through the Oort Cloud move extraordinarily slowly relative to the Sun. At that distance, the Sun's gravitational pull is so weak that a single nudge, a passing star, a molecular cloud, a slight gravitational fluctuation from the galactic plane is enough to redirect one of them inward. That journey, once begun, takes thousands of years. When a long-period comet finally arrives in the inner solar system and becomes visible in Earth's sky, it is completing a voyage that began before recorded human history. The ice on its surface has been sitting undisturbed at temperatures close to absolute zero for billions of years. We are, in a very literal sense, watching something ancient and unchanged fall toward us from the edge of the solar system for the first time in its existence. Those comets also carry information. The composition of Oort Cloud objects reflects the conditions of the early solar system. The chemistry of the disk that formed the planets, preserved in ice for 4.5 billion years. When one of them passes close enough to the sun to develop a tail, the material it sheds is a direct sample of what the solar system was made of before any of the planets existed. Studying them is as close as we can get to reading the original recipe. But the Oort Cloud is not just a relic. It is also a record of violence. The objects that populate it were not formed there. In the early solar system, the region between and beyond the giant planets was far more crowded than it is today. Jupiter and Saturn, as they settled into their final orbits, acted as gravitational slingshots, redirecting enormous numbers of smaller objects outward at high velocity. Some were ejected from the solar system entirely, lost to interstellar space. Others were thrown outward with just enough energy to escape the inner system, but not enough to escape the sun's gravity entirely, eventually settling into the slow, distant orbits of the Oort Cloud. The sphere we see today is the accumulated debris of that early period of planetary migration. Billions of objects flung to the edges of the solar system and left there, slowly orbiting in the dark. It raises a question that doesn't have a clean answer yet. If our solar system ejected material outward during its formation, so did every other solar system, which means interstellar space, the void between stars, should contain a population of objects that were ejected from their home systems and now travel freely through the galaxy, belonging to nothing. In 2017, we detected the first confirmed interstellar object passing through our solar system. It was named Oumuamua. It came from outside, moving too fast to be bound by the sun's gravity, passed through the inner solar system, and continued outward. Where it came from remains unknown. What system formed it, how long it had been traveling, what it encountered on the way, we have no way of knowing. It was through and gone before we fully understood what we were looking at. The detection of Oumuamua changed something in how astronomers think about interstellar space. If one object passed through in the period we happen to be watching, statistical models suggest interstellar space is full of them. A slow, invisible current of material exchange between solar systems over billions of years. The boundary between one solar system and another is not a clean line. It is a gradual transition, and the material drifting through it carries the history of multiple stars. This matters for a question much larger than orbital mechanics. One of the oldest debates in astrobiology is whether life, or the chemical precursors to life, could be transferred between solar systems, carried inside rocks or ice, ejected from one planet, traveling through space, and eventually arriving somewhere else. The process is called panspermia, and for most of its history as a hypothesis, it has been treated with a degree of skepticism, largely because the distances involved seem to make it implausible. The detection of interstellar objects moving between solar systems makes it somewhat less implausible. Not confirmed, not even particularly likely given what we know, but no longer obviously impossible in the way it once seemed. There is a final dimension to all of this that the flat diagram never captures. The solar system is not sitting still while all of this unfolds, it is moving. The sun, carrying all its planets and their moons and the entire Oort Cloud with it, is orbiting the center of the Milky Way at approximately 230 kilometers per second. One complete orbit takes roughly 225 million years, a unit of time sometimes called a cosmic year. In the time since the dinosaurs were wiped out, the solar system has traveled less than a third of the way around the galaxy. In the entire history of complex animal life on Earth, we have completed roughly 2 full galactic orbits. But we are not orbiting flat within the galactic plane. The solar system is tilted approximately 60 degrees relative to the disk of the Milky Way, and the sun does not travel in a simple circle. It oscillates, bobbing slowly up through the galactic plane, reaching a maximum height above it, falling back down through it, dropping below and rising again. One complete oscillation takes roughly 70 million years. The solar system is not a spinning disk traveling in a flat orbit. It is a three-dimensional structure following a helical path through the galaxy, rising and falling through the galactic plane on a cycle longer than the age of the dinosaurs. During those oscillations, the solar system periodically passes through denser regions of the galactic disk, where molecular clouds and higher concentrations of matter create a slightly different gravitational environment. Some researchers have proposed that these passages correlate with periods of increased comet bombardment in the inner solar system, the gravitational disturbance reaching all the way out to the Oort Cloud and nudging objects inward. Whether that correlation is real and whether it has influenced the history of life on Earth through periodic mass extinctions remains genuinely contested. But the fact that we are even asking the question reflects how thoroughly the three-dimensional reality of the solar system's motion connects to everything that happens within it. The flat diagram has its uses. It communicates relative distances, orbital periods, the basic architecture of the inner solar system. As a first approximation, it is not wrong, but as a picture of where we actually live, it is missing almost everything. The real solar system is a sphere a light year across, tilted 60 degrees to the galaxy it moves through, following a corkscrew path through space at 230 kilometers per second, populated at its edges by trillions of objects that have been sitting undisturbed in the dark since before the Earth had oceans. The planets are not the solar system. They are a small, flat, well-lit room inside a structure that extends in every direction far beyond anything we have physically reached or are likely to reach within any timescale that feels meaningful to a human being. That is what it means to live in three dimensions.